Today I'm going to talk you through the exam style questions of the second part of the exam unit, Waves in Communication. Question 1. Figure 1 shows a pulse of light entering an optical fibre. The refractive index of the core of the optical fibre is 2.36, and assume that the optical fibre cladding, so that's what goes around our optical fibre, has a refractive index of 1. So part A is to calculate the critical angle of the boundary between the core and the cladding. So the core is what is shown in figure 1, it's what the light ray enters. In an optical fibre, the light ray should totally internally reflect all the way along the fibre and out the other end. So part A is asking us to calculate the critical angle, which is the angle at which, if the light hits above that angle, it will totally internally reflect. If it hits below that angle, it will just go out of the material. So for part A, we are going to use this equation. Sine C, so that's the sine of the critical angle, is equal to 1 over the refractive index n. So the refractive index for this material is 2.36. So we could just put 1 over n into our calculator and that would give us the sine of the angle, but we just want the angle. So instead, what we're going to type into our calculator to get the critical angle C is sine minus 1. So there is a button for that on our calculator. You have to press shift before you press the sine button. You'll then use your fraction key, 1 divided by 2.36, and then close your bracket. If you get any errors, it might be because you haven't closed your bracket, and that gives us an answer of our critical angle being 25.1 degrees. Part B asks you to complete figure 1 to show the path of light through the optical fibre. So you'd use a ruler for this, nice straight line, and it's going to bounce off around the same angle. So if you were to draw your normal in here, which is at 90 degrees, this angle of incidence should be equal to the angle of reflection. If you had a protractor, you could use that to measure it, but for now, you just do it roughly the same size. C is calculate the speed of light in the optical fibre. So what we're going to do there is we're going to use this equation, n, our refractive index, like the one above, is equal to C, which is the speed of light in air, divided by V, which is the speed of light in this material. So we know n, that's 2.36, and C is a constant. That means it's always the same. So that is the speed of light in air, which is 3 times 10 to the power of 8. So what you're going to need to do first is to rearrange this equation. So I would use a formula triangle if you're not comfortable rearranging. And to make our formula triangle, we look at our divide and you've got a C on top of a V. So we put a C on top of a V and then we've got our N left over there. So what we want is V. V is our unknown, the speed of light in our material, which is an optical fibre. So to use our formula triangle, we cross out our V and we look at what's left because V is what we want. And what we've got is V equals C divided by N. So C is 3 times 10 to the 8 and N is 2.36. So if you type that into your calculator, you should get 1.27 times 10 to the 8. Your calculator probably won't already group it together as a times 10 to the 8, so you get 127 and then quite a few other numbers. It'll be a big number. You can just write down that whole number as your answer on the test. And to double check whether our answer is right, you're looking for a number that is smaller than the speed of light in air, because your light ray will slow down in a different material. For part D, at the end of the optical fibre, light leaves the fibre at an incident angle to the normal of 18 degrees. We need to calculate the angle of refraction of the light. So as it leaves, the light ray is going to speed up again because it's going back into the air. Therefore, it's going to refract, it's going to change direction. So the equation that we're going to use is n equals sine I divided by sine R. So n, again, we already know is 2.36. It's the same throughout the question. I is the next thing we've got to look at, and that's our angle of incidence, which is 18. It's given to us in the question. The clue is incident here. That starts with an I. So the thing that we don't know is our R. That's what we're going to want to know. So again, we can use our formula triangle to help us rearrange this equation. So we'll look at our fraction. We've got sine I on top of sine R. So we'll put sine I on top of sine R, and that gives us an N left over. If our N and our sine R were the other way round in our formula triangle, that wouldn't make any difference at all. then I want sine r at the moment, so I'm just going to cross that out for a second so I can see what I've got. So sine r is going to equal sine I divided by n. So I could type that into my calculator and get an answer now, but it's going to be a decimal with lots of numbers. So instead, I'm going to finish rearranging before I even type it into my calculator. This would give me sine r. I just want r instead. So what I'd do, r would be equal, and I'm going to use my sine minus 1 button again. R is equal to sine minus 1, sine I divided by, not sine, divided by n. So you would type that into your calculator, and the numbers would be sine minus 1. So you'd write in sine 18, and you'd divide it by 2.36. And the answer that you would get, r is equal to 7.52 degrees. That's question 1 done. On to question 2. Question 2 here is about comparing digital signals and analog signals. So data on the whole is transmitted as a digital signal. Part A, describe the difference between them. So we're going to say an analog signal is continuous and a digital signal is discrete. Okay, and that means it comes in separate little bursts rather than being a constant flow. For part B, give 2 advantages of using a digital over an analog signal. So there's a few different options you could have here. You only need to have 2. So digital signals, sorry about that, a digital signal are high frequency. So transmit a lot of information quickly. You could have also had very little interference. That's in our digital signal. And there's no loss of signal over a large distance. An additional one you might have had is that multiple digital signals can be sent along the same cable. And then for C, this is describing how to convert an analog signal into a digital signal. So you would use a transducer to create an electrical signal. And this signal is going to be proportional to the signal that was sent. You're then going to connect analog output, so that's what comes out of our analog one, to a digital input. So whatever comes out your analog, you're going to make sure it goes into a digital input. You then select an appropriate sampling rate. And then you transmit your signal. So that's 4 marks there to describe that process.